Hi everyone. So before we start this particular section of the tutorial, I would like to strongly recommend that you look through the previous section where we had a pretty lengthy discussion on measures and drivers, because we are going to be drawing heavily upon the concepts and some of the terms that we used in that discussion during the course of this particular section. So this is going to be the final part of this tutorial where everything is going to fall in place. So we've already have created our segment one, and we already have an any revenue joint. Now over here, we're going to be using this any revenue joint as a measure, as was discussed in the previous section. And we're going to use a driver to actually drive this measure so that the joint rotates at, or the segment one rotates about the joint at a constant velocity. So for that, let us first have a look at the joint itself. So I can do this by double clicking on the name of the include file where I've defined a joint. This is joint.any. And you can see that this immediately opens up my any script file with the joint definition in it. So over here we have the class name, which was any revenue joint, and the name of the object of this class was ground underscore segment one underscore joint. Now, if I wanted to locate this particular object in the model tree, I can just, I don't need to highlight it. I'm just doing that right now to make it more readable for you. I just need to move my cursor over the name of that particular object, and then click locate in model tree. And if you check out the model tree on the left of the screen, you can actually see that that particular object has been highlighted. So we know that the joint exists, so the measure exists. So the next step is to create a driver for that measure. So we'll do this in a new AnyScript window, and I'll open a new one by using the button on the toolbar on the top. And when I click that, I get a new window that I will save right away. And I will call this particular file driver.any. Now in driver.any, there is the classes tab on the left, and I will open that tab and expand the class list. Now over here, the driver class that I'm looking for is the AnyKinEQ simple driver, which again you might remember from our discussion in the previous section on measures and drivers. So if I scroll down here, I will actually see that there's a series of these AnyKinEQ classes. All their names begin with AnyKinEQ. And all of these are different kinds of drivers, and I would urge you to check out what each of these do by using the reference manual. But the one that we are interested in for the moment is this one over here, AnyKinEQ simple driver. So I'm going to right click and say insert class template. So the first thing that it prompts me for is an object name, which just has some placeholder text at the moment. So I'm just going to call this the revolute underscore joint underscore driver. You can feel free to name this whatever you like. And then there are a lot of optional members which have been commented out with these double forward slashes. That's why you see them as green text. But there is one mandatory member, which is driver well. And we'll see what all of these different members mean in just a minute. But for now, I'm going to clean up most of these optional members because I just want the code to look nice. And I'm only going to leave one optional member, which is a class of type anykin measure. Now let us see what driver well and this, which is the name of the object, not the class of the object, and anykin measure, which is the class of the object and not the name of the object. The name is right here, and we are free to name it whatever we like. But let us see what these two members of this class actually signify. So for that, I'm going to move my cursor over AnyKinEQ simple driver, the class name, and hit F1. And this opens up my AnyScript reference manual, and it automatically opens up the entry for this particular class in the manual. So you can see that there, the anykin measure and our driver well are both way up in the list of members that this class needs. And you can see that anykin measure is an expected member. Now, an expected member is a member that is that you better provide. Now, if you don't do that, your driver is not going to do its job, because we'll see why in just a second. But your simulation is not going to crash. On the other hand, an obligatory initialization member is one which is absolutely necessary for your simulation to run as well. So it's not just for your driver to do the right thing, but also for anybody to accept your model in the first place. So let us see what both of these members actually do. So the first member, which is the anykin measure, is actually just a reference to the kinematic measure that has to be driven by this object, which is the driver. And it must be noted that you can provide any number of these measures. So which means that you can use the same driver to drive multiple measures at the same time. On the other hand, driver vel is just the velocity of the measure that is being driven at the time t equals 0. Now, in our case, we don't really have any acceleration. We're just going to try simulating constant angular velocity. And so this driver vel at t equals 0 will always be the same driver vel. And because our measure is the joint angle, this driver vel, which is technically dimensionless, in this case, it's going to be the angular velocity of our any revolute joint. So now we can shut the reference manual and go back to AnyScript with this new wisdom that we've just gathered. So driver vel was actually a vector. Again, I forgot to point this out in the reference manual, but you can go and look up the object type for driver vel, which would be a vector object. And in this case, this vector is just going to contain one term because the measure that we are driving, the revolute joint, is just a 1 degree of freedom. Which is a 1 degree of freedom joint. On the other hand, if we were driving a ball and socket joint using this driver, then this particular component, this particular vector driver vel would have 3 components. So right now we'll set the angular velocity of our driver or of the joint to pi by 2, and this is in radians per second. So this is going to be pi by 2 radians per second. And then as for the anykin measure object, do note that this ampersand sign indicates that this is just a reference to a measure that has already been created. So you're just tapping this particular driver object on the shoulder and saying, hey, the measure you're looking for is right here. And we'll insert the name of or the full address of the measure in the model tree. We'll insert that here in just a minute. So after this particular ampersand, there is some placeholder text for the name of this measure. And to demonstrate that I can use pretty much any name, I'm going to use my name over here. And then there's some more placeholder text, which is basically it just says that this is the name of the measure that we actually want to be driving. And if I turn your attention to the model tree, you might remember from some of our earlier actions in this section, we have already located the any revolute joint in the model tree. So all I need to do is note that I've already highlighted the placeholder text. So all I need to do right now is right click on this object in the model tree and say insert object name. And if you check out your AnyScript window right now, you can see that the address of this particular object in the model tree has now been inserted. So our driver is actually ready. So I can now save this file, and I will just be closing this file right away. Now my next step is to tell my main file that the driver has been created, and you can look for it in driver.any. And I do this using this include statement. I can ensure that I'm referring to the right file by double clicking on the file name and just ensuring that the file that we just created has been opened. Just one thing that I just noticed right now from my action just a few seconds back is I forgot to put a semicolon at the end of my statement. And this I would like to mention is very important. All your AnyScript lines of code, except of course a few exceptions like include statements, all of these should always end with a semicolon. So now I can close driver.any again. So now we have all our model components ready, and all these model components are contained within the any folder object that we've called model. And you can see that the scope of this any folder object is given by these two curly braces. So let us actually go outside the scope of this any folder object, outside the lower curly brace, create some space over there, and create a new any folder object, which will hold our analyses that we want to run our model components through. So this folder I'm just going to call simulations, and I'm going to call it just put equal to, and this is just our standard syntax. Now all our components of this any folder object will basically go in here, and they will all appear as a separate branch of the model tree. So as for my simulations themselves, I will be including them after creating them in a new AnyScript file. So I've opened this new scripting window using the toolbar button, using the button in the toolbar, and I'm going to save this file right away as studies.any. Now, the reason why I've called this studies is because in Anybody, the analysis or the simulation that we run is called a study. So if I look at the classes tab on the left now, I can expand my class list, and right at the top of this class list, you will actually see a class that is named Anybody Study. And this is the class that helps you run these studies or create these studies or simulations, as you would call them, uh, in Anybody. And these can then be run later, as we will see. So I'm going to right click on the Anybody Study object and insert the template for this class. Now just brace yourself because this template is massive, and that is because by default Anybody just sets the values for many of these study parameters such as optimization tolerances or kinematic assembly errors and so on, but it gives you the option of changing them if you want to, and that is the reason the class template just assumes that you want to change or you want to set every particular member of this class. So let us do away with all of these optional parameters that are just sort of cluttering up our code. And I'm going to take out all the optional parameters except just a few, and I'll talk you through them in just a second. There was gravity down here, which wasn't an optional parameter. Just want to point that out. And that is actually a mandatory parameter. So let us see what these optional parameters are. So there is t start, which is the time at which your simulation analysis begins. We will set this to 0 seconds. And there is t end, which is the time at which your simulation ends. And I'm going to set this to 5 seconds. And then there is end steps, which are the number of time steps you want over the entire course of the simulation between t start and t end. And I'm just going to set this to say 200 right now, which means I'll have around, because given that I have 5 seconds of time, there's going to be around 40 steps per second. Gravity is a vector, and that is your gravity vector that I'm going to set to 0 along the x direction, negative 9.8 in the y direction, and this unit is in meters per second square, and 0 again in the z direction. So this means that gravity acts along the negative y direction. My Anybody study needs a name, and I'm just going to call this my one segment, segment study. Now there's one more object that we need to, or one more member that we need to include in this class, and that is, now this particular study that we've created, it's a study in itself, but then it hasn't been assigned any model components to run through it or to pass through through its analyses. And so we need to create a reference to the any folder object which contains our model components. So I'm going to do any folder followed by the ampersand sign, which of course means that we're going to create a reference. And I'm just going to call this the to ref, which is a reference to model folder equals. And now I'm going to turn my attention to the model tree on the left, where I will go all the way up. Now we know that this particular model folder contains all my model components. So I'm just going to right click over here and say insert object name. And the moment I do that, I can return to AnyScript, and I can see that the address of my model folder in the model tree has been inserted in full. So main.model, and I end this with a semicolon. So now my study is actually done as well. Now I can close this file, and now I need to tell my main AnyScript file that I've created this study in a separate file that I've called studies.any. I can confirm that this is the right name by double clicking on the file name, and the file that we just created the study in has opened. I can close this. So now our model is ready. So now we have our segment, the joint, we have a driver for the joint, and we have a study down here to actually analyze the model that we've just created. So I'm going to just go ahead and load this model by clicking the button on the toolbar at the top. And if I draw your attention to the model window, or sorry, the message window at the bottom, you can see that this model has been loaded successfully. So now I go to Window and Model View. So now we still, there still doesn't seem to be any change really. We still just see the segment floating around in space, but this is about to change very soon. So let us have a look at this section on the left of our screen where we now see the model tree. Now earlier in much earlier in this tutorial series, I had mentioned that there were other tabs over here, one of which was operations. Now when we open operations, you can actually see that you have a more refined version of the model tree over here. And it's refined because it has this model tree does not contain any of the model components. It only contains the simulation components that have been filtered out. So if I expand this, you can see the study that we've created, one segment study. And in there, you can actually see the names of the different analyses that come along with the study. Now, these are initial conditions, kinematics, and inverse dynamics. Now, initial conditions just does a kinematic assembly of your system at your initial time, that is t equals 0 in this case. Kinematics runs a kinematic analysis, while inverse dynamics will run kinematics as well as compute the forces that it takes to sustain the given kinematics. So this is the most advanced study that you have. So we will be running this study right now. So I will first click on inverse dynamics, and then you will see that the buttons on the top of your toolbar, on the toolbar at the top, these buttons that had been completely inactive so far have suddenly jumped to life. You can see them turning black instead of gray. Now I have to click on inverse dynamics and then go and click the play button that you see over here, which says start operation. Now the moment I do that, you can see that in the model window, your model has started moving. On the bottom left, you can actually you can see the status of your simulation in real time, which right now it has finished running, so there are no updates over here really. And down here in the messages window, we see a few warnings. And this just states that there really aren't any muscles in our model, which is completely fine in this case because we didn't intend to have any muscles. If I want to see that motion again, I can go back to the operations tab and click on replay and then click the start operation button again, the one that looks like the play button. And this is not really rerunning the analysis, but it's just recreating the motion for you to just go over again. So now now you have a visual representation of the motion, but let's say we want to talk numbers. So for that, let's assume that I want to either find out what the joint reaction force is at this revolute joint, or let's say I want to find out what is the torque that is needed to sustain this motion, or what is the joint moment needed to sustain this motion. This picture wouldn't tell me any of those. So for that, I will close the model view and I'll go back to Window, which is the drop-down menu on the top, and go to Chart 2D/3D. Now this opens up a completely new window which has a completely empty graph over there. But on the left of this window, you will see that again you have your model tree, which has been filtered out. It doesn't show your model components, it only shows your simulation components. Now I can just keep expanding this particular tree till I get to this folder that is called the output. So this is the output of the study that was one segment study. And in this output folder, you can see that it has the three different studies that we ran, that we could have run, although we only ran inverse dynamics. And over here we have a reference to the model folder, upon expanding which you can actually see that I can see all the three model components, my segment, my joint, and my driver here in this mini model tree. So let's say I wanted to see what was the torque required for the driver to actually sustain this motion, to basically keep the segment rotating at constant angular velocity in a vertical plane against the action of gravity. I can expand this, and over here there is another subfolder called reaction. And in reaction, there is a term called F out. Now, if I click on F out, that graph has been loaded, and as would be expected, it sort of follows a sinusoidal or a cosine in this case, I guess. So it follows a cosine trajectory, which is what we would expect. And you can always change the abscissa for this particular graph. By default, it is the time vector of our study, but this can be changed if you want to plot, say, the joint torque versus angular velocity, for example. Or you can try a lot of different things with this. So I would leave it to you to go ahead and experiment with that. So this was the torque needed at the joint or the joint moment. I will now go back to my mini model tree over here, and I'm going to close this folder and now expand the folder that corresponds to my joint. Now in here, you can see that there is a subfolder called constraints, and in constraints there is again another subfolder called reaction. So this folder contains the force values, which are essentially the forces needed to maintain the constraints of the joints, and these forces are hence the joint reaction forces that you're looking for. So if I click on F out, which is the output force, you can see that there are three different graphs over here in red, blue, and green respectively, and these represent the X, Y, and Z components of the joint reaction force. I would leave it to you to sort of explore this chart window a little more. You can find more about this in the written tutorials, which you can find by clicking on Help and Tutorials. So over there, you can find more information on the chart window. But just one last cool thing I would like to leave you with is this particular button up here. So I can actually click on this button, and this immediately opens up a table at the bottom of my chart window. You can see over here, which actually contains the values of the values that correspond to these graphs that have just been plotted over here. So on that note, I would like to congratulate you on the completion of this basic Anybody tutorial. I think you essentially have all the building blocks it takes to become an expert modeler using the Anybody modeling system. And as you will progress, you will also see that the possibilities just keep growing and almost seem endless when it comes to building more complex models. And I'm pretty sure whatever we learned about measures and drivers and so on will excite you a lot more at that stage. So I would encourage you to follow the written tutorials and also keep checking back at our YouTube channel to check out more cool tutorials for anybody. Thank you.